we're going to study rate laws, chemical kinetics, in terms of the decomposition. Decomposition of blue. Let's see, which one is it? Blue number 2. I used to have, when I had a large enough class, half of the class blue number 1. Blue number 1 died. Half of the class would do blue and the other half would do red, but the classes have shrunk so much, everybody does blue. All right. Decomposition of blue number 1 reacting with bleach, chlorine bleach, which is sodium hypochlorite. Okay, so in this case, we do have 2 reactants. Okay. Our objective is to determine the rate law. Oops, ahead of myself. The rate is equal to some value K times blue number 1 to its order and sodium hypochlorite to its order. That's our objective. We want to find out this value, that value, and this value. Okay. Let's see, before we do the pre-lab questions, there's your safety blurbs. I will say this. How are we going to track the concentrations? Well, the bleach, the sodium hypochlorite, is going to be the one that we have in large excess. Like I mentioned earlier, large excess, so this one doesn't change during a reaction. And we allow this one to change. But how are we going to track the disappearance of the blue number 1? Right? Well, what the bleach is going to do is what we call, it's going to decolor it. In other words, it won't absorb and give you the blue color anymore. So we have a wavelength of absorption for the blue, max absorption is equal to, and I think I put that in here. I hope I did. Come on. There it is right there. Oops, too far. Sorry. There it is. Blue number 1, 630 nanometers. So we're going to use a spectrophotometer, and the reaction itself is going to occur in the cuvette. That is the little glass or plastic container that goes into the spectrometer. So we're going to watch it over time as it progresses, and the absorbance of this, we're going to substitute here. The absorbance is going to decrease gradually as the blue decolors. So this is the value that we're going to use to express our concentration of blue number 1. It's not going to be in molarity, it's going to be in absorbance units. Now this concentration is going to be in molarity, and that's why the pre-lab questions, one of them discusses or requires that you calculate the molarity. Okay. So that, as a practical matter, that's how we're going to track things. Let's go back up and do the pre-lab questions now. Here we go. All right, the first one. Pre-lab number one. A container of household bleach has 5% sodium hypochlorite by weight. So our bleach is 5%. I think it's weight, or maybe it's weight volume. I think it's weight of sodium hypochlorite. Okay. What we want to know is what is the molarity of that solution? And we know the density of that solution is 1.08. Density equals 1.08 grams per milliliter. All right. We know we want molarity, so that is moles per liter. We know then also that we have 5 grams of sodium hypochlorite per 100 grams of solution. Okay. That's mass per mass. We need moles per liter or moles per volume. So that's where the density comes in. We can convert that into an equivalent for volume by saying this is grams of solution. So 1.08 grams of solution per milliliter. But that needs to be in liters, doesn't it? Right? We got rid of grams of solution. Now we need milliliters of solution, liters of solution. So we need liters on the top, milliliters on the bottom, and we have 1,000 milliliters per liter. Okay, so, oops, my mistake. I had it right the first time. Liters is going to be in the denominator. There we go. So that cancel. Now we have per liter. Now we need to change grams of sodium hypochlorite to moles. And that always means molar mass. What's the molar mass of sodium hypochlorite? Well, sodium is 23.00 grams per mole. Oxygen is 16. And chlorine is 35.45. 40. So I add those together. Is 74.45. So 74.45 grams per mole. And that cancels the grams and gives us moles per liter. Okay. So that's the thinking part. Now it's just crunching numbers. So 5 times 1.08 times 1,000 divided by 100, right here, and divided by 74.45. So that's 0.725 molar. Okay. Now, this example is for 5% sodium hypochlorite. In our experiment, we're going to be using 6%. So you need to be able to calculate what is the concentration of the bleach of the sodium hypochlorite in 6%. So what would you need to do? Just change that to 6, right? Change that to 6 and recalculate. And that'll give you the concentrated version, 6% of sodium hypochlorite. Now, when you put sodium hypochlorite into the experiment, you're only going to use a few drops of it. So that requires another calculation, but this is your starting point. Okay, so that's number one. Let's do number two. All right, how many grams per liter of sodium chloride are required in order to prepare a solution with a concentration equivalent to the solution in question 1? All right, I shouldn't have erased that. What was the value? 7.725. Thank you. 0.725 molar. Okay. Now, why do we need a solution of sodium chloride? Because one experiment is going to be with a certain amount of sodium hypochlorite in solution to decolor the blue. But we need another concentration that's less. We're going to go half that concentration. But we need to make up the difference with something that gives us the same ionic concentration as sodium hypochlorite without the bleaching effect. And that's sodium chloride. And we'll make up the other half. We're going to use half as much of this and make up the other half with sodium chloride. Well, the sodium chloride needs to be the same concentration as the bleach, because if we put, say, 10 drops per cuvette of the bleach for our experiment, then we want 5 drops in the second experiment of bleach and 5 drops of sodium chloride. But they need to be exactly the same concentration to maintain the balance. So that's why we want to calculate how do you make that solution out of sodium chloride. Okay, this is going to be moles of sodium chloride per liter. Okay. So how many grams per liter would that be? Very simple. We've already got the right volume. We just need to change moles to grams. Right? Sodium chloride would be 23 for sodium and 35.45 for chlorine, or 58.45. There we go. So, oh, there it is right there, my calculator. 0.725 and 58.45 times. So that's 42.4 grams of sodium chloride per liter. That will give you the exact same concentration of sodium chloride as sodium hypochlorite. Okay. Now you'd have to do the same calculation for 6% sodium hypochlorite, because you're not going to use 5%, you're going to use 6%. So that requires a separate calculation to actually perform the lab. Okay, number 3. What is the percent of sodium hypochlorite by weight for a liter of bleach that is 0.8 molar sodium hypochlorite and has a density of 1.09 grams per mil? These 1, 2, and 3, all of these are dimensional analysis type problems. So what's the percent by weight of sodium hypochlorite? This is going backwards. We went one direction for number 1. Now we're going backwards for number 3. So 0.800 molar is moles of sodium hypochlorite per liter of solution. Right? And since the density is in grams per milliliter, this has to be converted back to milliliters. Right? Liters here, milliliters there. So that's 10 to the third on there. Takes care of that. Now what we need is, what's that in grams? And I didn't write it down. The molar mass of sodium hypochlorite. And calculate it again. 23, 16, and 35.45. 7445. So this is 74.45 grams of sodium hypochlorite per mole. Okay. Now that we've got grams per milliliter, we can convert milliliters of solution to grams of solution. So we need milliliters on the top, because this is in the denominator, that has to be in the numerator. And that's 1.09 grams per milliliter. Now the milliliters cancel, and we've got grams of solution. Well, actually, that's only for 1 milliliter. What would it be for 100 times that? Let's see. That only gives us, oh, okay. I think we can work it this way too. So 0.8 divided by 1,000 and 74.45 times and 1.09 divide, and that's 0.0546, and that's a fractional. So what we want is multiply by 100. So 2 to the right would be 5.46%. This is the fraction in terms of grams of sodium chloride per gram of solution, but we want per 100 grams. So we would multiply by 100. So I could have done times 100 here, and that would give me that value. So it's 5.46% by mass. Okay. So you need to set up your notebooks so I can check them. Let's see. The first step in the experiment is how much bleach? How much bleach to decolor? It's in the hallway. They moved the trash can in the hallway. How much bleach is required to decolor your blue color? So we're going to have a certain concentration of the blue color, and that's already been prepared actually, so that you don't go over the limit of your spectrophotometer. And then you want to test how many drops of your bleach are required to decolor in a certain number of seconds, a certain number of minutes. I think it's 2 minutes. And then that becomes the amount of your full strength sodium hypochlorite. And then we take half that number of drops for the half strength. Okay. So that's the first step. You got to determine that. And then, let's see. One second. Okay. Then you're going to take absorbance measurements as you go over every 10 seconds. You take an absorbance reading. So you got to be quick because you want to get those absorbance readings as close to the beginning as possible. Oh, a word about why we can use absorbance. What does absorbance mean? Okay, what we're referencing here is the Beer-Lambert law. So an absorbance, well, actually, you've got two ways to express the absorbance of light in your spectrophotometer. One is percent transmission. This is nonlinear. We don't want to use that one. So we've got an absorbance, which is a logarithm of that value. So absorbance is equal to several factors. One is I like to say absorbance is A, B, C. A is the absorptivity of your chromophore. That is whatever absorbs the light. We don't know what that is. Well, you can't look it up, but we don't need it. B is the path length. In your case, the path length is 1 centimeter. And C is the concentration. Okay. Now, since absorptivity is not going to change because we're measuring the same molecule and the path length is constant, then absorbance varies with concentration directly. That's why we can use absorbance. Do you need to go?
Yeah.
So we're going to use absorbance instead of concentration, and we know that according to Beer-Lambert law, that the value of absorbance is a good approximation of the concentration. So this is, instead of blue number 1, this is going to be absorbance of the blue dye to the nth, to this order. And then the sodium hypochlorite, we're going to get 2 sets of data. And then when we have those 2 sets of data, remember what we do with the data? When we talked about it in the lecture, it was actual molarity, but we're going to have time as one factor, and then we're going to have absorbance as the other factor. Okay, for the full strength bleach, how do we determine the value here? Okay, we need to plot time against absorbance, time against the natural log of absorbance, and time against 1 over absorbance. And see which one of these is linear. That will tell us that value right there. At that point, we will have an expression that says rate equals K prime, absorbance to whatever the N is. But K prime is not our final answer. We want K. So we have this one for full. And we're also going to do another experiment with half strength. Like TA and then log A and 1 over A. All right, we're going to have this one for full strength, for half strength. Okay. And this should verify that we have the correct one here. So we're going to have a different K prime for each one. We're going to have a K prime for half strength. But the N should be the same for both of them. Okay. But we have 2 different K primes. Now, what is that K prime equal to? Well, the K prime for this one is K prime for the full is equal to our actual K times the concentration of that to the M. Okay. And the K prime for the half is equal to our K times this one. Okay. We want to get at that K. But first we need to find out what this is right here. Right, we're gonna have a value for K prime and a value for K prime half, full and half. So if we do like our initial rates and ratio them like this, then we get a value here. The K's cancel. And these are two different concentrations. So we're going to get a ratio. We're going to get this value here is equal to a ratio of these two to the m power. This is full. This is half. So we're going to get a full and a half ratio there. So we get a value here, we get a value here to that power, and we can solve for that power right there. Now that we have that power, then we can substitute it in here. We'll have this one, we'll have this one, and we'll have let's see. Oh, once we have this value here, we can plug it in there, and we have this value, and we have this value, that value, that value. We can solve for K. We can use either one, it doesn't matter. Now that we get K out of that, first we get the order out of it, and then we go back to one of them and we find out what K is. Once we have the order, we can plug it in there. We have this value, we have that value, we can solve for K. Now that we have K, we can write our full expression. K here, blue to that order, sodium hypochlorite to that order. That's where we're headed. I know that's a lot of math, and that's why at the end of the document, well, there are post-lab questions there. But, at the end of the document, I've got, okay, here's an example of calculating the molarity of bleach in the reaction vessel. That's what we need for here, here, and here, two different values. And then this is an explanation of what I was talking about here, ratio those two, and end up with, in this example, you end up with a value here that is not an integer. Right, so don't be dismayed if your calculation gives you a value here that's not an integer. This one will be an integer because we determined that one from our graphing. But the calculated value for the order for the bleach is likely not going to be an integer. Okay, so there's what the expression would look like for this example. And I think that's it, yeah. Okay, any questions? Okay. The experiment itself, it requires coordination. Right, got somebody that's actually, because when you finally set up your experiment to occur in the spectrophotometer, the last thing you add to the mixture in that cuvette that's in your spectrophotometer is the bleach. Because once you add that bleach, it starts to decolor. The reaction is very quick. So you want to get it in there, mix it a little, and then start reading. And you'll see the absorbance values decrease over time. Of course, when you use half strength bleach, it's going to be slower. It's easier to manage, but still, it's pretty quick.